Hello everyone, I am Aljaber Mahmood. Our paper is titled Mutual Adaptation in Human-Robot Co-Transportation with Human Preference Uncertainty. In this video presentation, we show how we design the experiments and validate our proposed framework. At first, to map human preference uncertainty into probability distribution, we need to obtain the value for the weight that determines the relative importance of collision risk versus travel distance. For that, we presented four environments to human participants. They rated their likelihood of choosing each path option in percentages. The trajectories through openings are not visualized so that participants do not get any extra information. By tuning the model with this data, we identified CR equals to 10. The table shows the human provided percentages and corresponding model predictions in parentheses, confirming close alignment in the validation environment. Then, to obtain the individual sensitivity parameter for stubbornness and mode transition mechanism, we created videos illustrating robot-led progressive trajectories and asked participants when they wish to take control. We recorded the time steps of mode transitions from the robot-led to human-led. From these experiments, we identified three different values that reflect sensitive, medium, and less sensitive. For the sensitive individual, transitions occurred early, resulting in the human selecting the same opening as the one in which robot always passively adapted with no model. With medium and less sensitive individuals, the robot successfully influenced the humans to adopt initially robot chosen path. These results show our model effectively guides the human robot team towards safer and more efficient paths. After the mode transition, when the human is leading the team, the robot is uncertain about their exact path choice. To remain prepared, the robot employs pose optimization, adjusting joint angles while maintaining the same end effector pose to minimize costs across all possible paths. We show a hardware demo using Fetch Mobile Manipulator, and for that we set up an environment that contains three obstacles, creating two distinct path options, one with narrow opening but shorter distance and another with wider but longer. We first present a simulated demonstration where the robot initially leads considering human choice probabilities and increasing stubbornness. As the team nears the narrow opening, the increasingly stubborn human takes control indicated by a rotation. Despite initially preferring the wider path, at mode transition the human selects the narrow opening. Using the fetch robot, we demonstrate two scenarios, one where the robot passively adapts, resulting in the wide path, and another initially robot-led scenario where the human eventually leads with the increased stubbornness, choosing the narrow opening. At and after this transition, the robot continuously adjusts joint angles to prepare for uncertainties effectively. Due to limited space, we did not perform a rotation to represent the mode transition of the robot.